Pre-Calculus. We are back once again, and I have to apologize for our previous live stream. Partway through, about maybe an hour, hour and 15 minutes in, we lost my audio on my microphone, and so the last phase of that video is just mute. It's just me talking. You can't hear anything. You can only see my mouth moving. So my apologies for that. That was a technical issue on my streaming platform over here on my side. So my bad. My goal for tonight's slightly more abbreviated live stream is going to be to go back over that stuff that I was wordlessly telling you about during the silent portion of yesterday's live stream. And in particular, what our agenda is for today is to study how the properties of a graph of a function in pre-calculus are reflected by the formula for that function. And in particular, if I know the formula for a graph that makes a certain shape, how can I change that formula to make graphs of differing shapes? So that's the topic of graph transformations. It's really, I feel like, the biggest new sort of exciting, important skill in the first chapter of pre-calculus. It's something you probably definitely haven't played with in your previous algebra classes. And once we get our hands around how transformations work, in other words, how doing simple geometric things to a graph is reflected in the formula for the function of which that is a graph. Once we nail that down, we'll also be able to talk about symmetry properties that graphs, and then by extension their functions, have. In yesterday's live stream, we talked about these topics the other way around. We talked about symmetries first and then transformations second, but I think with the benefit of hindsight and the opportunity to do this once again today, I think it's a better idea if we start at the end of yesterday's story by first talking about transformations. How do we move graphs around in location, change them in shape and size and orientation, and how is that reflected in a formula? Talk about that first, and then we'll be able to use that understanding of graph transformations to also motivate how we understand graph symmetries. So that's the tack that we're going to take with it today. So our first priority here will be to talk about graph transformations. So if you give me the graph of a function, how should I supply the graph of a similar but related function? So there's three different types of graph transformations that we talk about in pre-calculus, and those three types are listed right over here. The first one is the simplest one. It's the one we're going to talk about first. It's called a shift. And in a shift, the location of a graph changes, even though the shape or size or orientation of the graph do not. So all we're doing is moving the graph around on the graph paper. Those are called shifts. And they come in two flavors, as will all of our transformations, a horizontal flavor and a vertical flavor. The second operation we can do to a graph is one that doesn't change its basic shape, but it can change how wide or how narrow or how tall or how short that graph is. So those, what I call shrinks and stretches, mathematicians in geometry would call them dilations. Those are done with a different kind of arithmetic to our functions and their formulas. And so we'll study how to do those as well. And then lastly, we'll talk about reflections. There are simple things we can do to the formula of a function in order to effect on its graph either a vertical reflection, so a reflection over a horizontal axis, or a horizontal reflection, that is, a reflection across a vertical axis. Right? And those are both called reflections, so they come in two flavors, horizontal reflection and vertical reflection. Sometimes in place of reflection, I call them flip, if I feel like saving some syllables. So these are our 6 types of graph transformations that we're going to talk about together today, sort of one at a time. So let's get started with the first of them, which is how do we effect a shift? How do I move a graph horizontally or vertically on the graph paper without changing its shape and without changing its size in any way? So the first thing to know about shifts is that there's a difference. Let me start that sentence over. The first thing we want to know about shifts is that they're the simplest kind of transformation that we can do to a graph. Let's take a quick look here at an example of what I mean by a horizontal shift. So by a horizontal shift, what I mean is taking a basic graph. So I'm going to start with this basic graph of a parabola over here, y equals x squared. And let's say that I just want to take that graph and I just want to slide it over to the right. Let's say I want to shove this whole graph over to the right by 6 units, so that the point which on my original graph was the point 0, 0, will correspond on my new graph to a point whose x-coordinate is 6 units higher. It would be 6, 0. Right? And the same is true for all of the points on my graph. Every x value on my transformed graph is going to be equal to the corresponding x value from the original graph, just added 6. Okay? So how are we going to come up with a formula to describe this graph? Well, the secret is to think about what's happening in my function machine. I'm going to sketch that function machine we talked about yesterday for a little bit. I'm going to just sketch a copy of that over here, just to kind of motivate our discussion. So we think of a function as being like a little machine, and the input that this machine takes is something that we often call x. The function itself is the box, the machine, call it f, and it produces an output, and the output that it produces is what we give the name f of x. Right. So this is schematically what a function is doing. It's taking some input, it's doing something to the input to produce an output. Right. So if we think about what equation this purple translated graph here should have, if I feed my function machine the x value 7, then what I need my machine to do is I want it to look up the y value of the point on the original graph that corresponds to 7. So the first thing that I'm going to need to do is turn that 7 into a 1. How do I turn a 7 into a 1? In the same way that I would also turn a 6 into a 0, or an 8 into a 2, or a 5 into a -1. How do I turn those latter values into those former values? The answer is subtraction. To turn my 7 into a 1, what I really want here is to subtract 6. Okay. And then once I've subtracted 6, I should just run that value, which is now the x value on my original graph here, through my function one more time to get the y value that we then transport back to our translated point. So, all in all, what could we say is an equation for this purple graph? Well, what's happening is that all of the x values that I provide this function are having 6 subtracted from them before they are run through the f function. And so what I can conclude is that this purple graph, I'm just going to kind of try to write this up here, the purple graph that we're seeing on the screen here has the equation y equals f of x minus 6. Right? If I'm putting an x into my function, I'm subtracting 6 from it, and then I'm running it through f. Okay? Where my original graph has the function y equals f of x. So what we might be able to conclude is that subtracting 6 from my values of x affects a rightward shift by 6 units. And indeed, that is the case in general. How do I shift a graph in a horizontal direction? What I want to do is replace the value of x, replace x by x minus something. So here I'm going to write it as x minus h. I'm going to write h here. And what that does is that shifts to the right. It shifts the graph to the right by h. Okay? So that's the first kind of transformation that we're going to cover here, is how do I shift a graph horizontally? If I want to shift my graph to the right by a certain number of units, I should subtract that number of units from my value of x and replace x in my original function with that. What would I do if I wanted to shift left? Well, if I wanted to shift left, I would just replace h by the opposite of h, and that would have the effect of replacing this minus by a plus. So before we move off of this horizontal shifts example, let's tidy this up a little bit by also saying that if we have x plus h, we should think of that as a shift to the left by h, rather than a shift to the right. So this is the first of our transformation types. If I want to shift a graph horizontally, I should replace x by x plus or minus h, where h is the number of units that I want to shift that graph either to the right or to the left, respectively. So coming back to the graph that we were just looking at, right? If my original graph here is y equals x squared, my new graph is y equals x minus 6, the quantity, squared. So y equals x minus 6, quantity squared, is how I get that purple graph over here on this side, right? So here I have shifted my original function to the right by 6 units, by subtracting 6 from my x's. So that's how I shift a graph horizontally. What do we think we need to change here if I want to shift the graph vertically instead of shifting it horizontally? I want to shift it up or down rather than left or right. What should I do differently? Well, the key there just lies in the difference between what horizontal on a Cartesian coordinate plane means and vertical means. Anything that happens horizontal in a graph is going to be something that happens to my x values. Some change that I make to the x values is what's going to affect a change that happens horizontally. So of course vertically we can affect changes by attacking the y values instead of attacking the x values. So the first thing you'll notice about this little chart is that everything that happens horizontally is a change we apply to x. Every transformation that happens vertically is a change we apply to y in the equation, which defines the locus of points on the graph of our function. So with that frame in mind, let's think about what we might need to do to effect a vertical shift. So now instead of a horizontal shift, I want to talk about what about a vertical shift? Okay, how are we going to make that happen? We know now we need to do something to the value of y, but what? So let's come back again to my y equals x squared basic shape. Let's say I want to take this graph over here, and I just want to push the whole parabola up by a certain number of units. Let's pick, I don't know, 3. Let's say I want to push this graph vertically up by 3 units. So I just kind of want to grab this point here at the vertex, this 0, 0, and just want to tug it north by 3 units. How can I do that? Well, I get this purple graph here once again. And what I've done is I've done something to all my y values. For a given x value on my translated graph, what I want to do is plug that x value into my original function. That gives me my original y value. And then take that y value and just add to it. Just add 3 to it. So if the original y value was 0, my translated y value is going to be 3. If my original y value was 1, my translated y value is 4. Original is 4, new one is 7, and so forth. So all of my new y values are occurring at the same x as they used to, but they're occurring at 3 units higher than the original y. So there's a 3-unit separation between all of these corresponding pairs of points. So what have I really done there? If I want to know how the new y relates to the old y, I'll kind of try to write this over here. New y subtracted by 3 gives me the old y. Right? And so another way of thinking about what's happening here is I can think of this translation in the same way that we thought about translations shifts talking about the x value. We can think of this as, again, a replacement. And the replacement that I'm going to make is I'm going to replace the value of y in the equation which defines the locus of points, which is the graph of my function. Replace y by y minus 3, or y minus k, let's say. If I replace y by y minus k, what this is going to do is it's going to shift my graph up. According to the example that we just did, it shifts us up by k units. But you might say, and you'd be right to say it at this point, in my graph it doesn't look like there's a y. I haven't written a y anywhere. I wrote f of x equals x squared. But keep in mind how we define the graph of a function in the first place. The graph of a function is defined as the set of all points whose y-coordinate is equal to f of the corresponding x-coordinate. So this is really, f of x is just standing in for y. So instead of f of x equals x squared, we can think of it as y equals x squared. And so with that frame on it, what I'm really doing is taking my original curve, which has the equation y equals x squared. Right? That's the red curve that's on the graph over here. And if I want to shift this thing up by 3 units, well, according to this, what I should be doing is replacing y by y minus 3. If I replace y by y minus 3, I'm going to nudge that graph up by 3 units. Y minus 3 equals x squared. Okay, but because we're looking at the graph of a function, we like to have y by itself so that we can understand what is the function of which this thing that we're looking at is a graph. So before I finish this example, typically what an algebra textbook will do is it will solve this equation for y. And when I solve this equation for y, I add 3 to both sides, and I find that y is equal to x squared plus 3. And this is the way in which I think we most often see it in algebra and pre-calculus textbooks, right? That rather than thinking of an upward shift, as I'm doing here, rather than thinking of an upward shift as something I want to subtract k in order to effect, I can instead think of it as adding 3, but adding that 3 to the other side of this equation. So I add it to the function. So here's how I want to say this. One way of thinking of this, this thing that we're doing here, is we're replacing y by y minus k in order to shift up by k units. But the way in which you're probably used to thinking about this is, instead, we can think about adding k, add k, outside of the function, outside of f of x. And what that does is it will shift up by k. So if we go back to this example, this purple curve is going to have the equation. On the one hand, we can think of it as y minus 3 equals f of x, right? Y minus 3 equals x squared. But the way in which most textbooks think about it is they just take that minus 3 and they move it from the left side of the equation to the right side. And now we can kind of see the story that this thing is telling, right? That if I take a function y equals f of x and I take its graph and then I add 3 to f of x outside of the function, all my y values are going to move up by 3, and that affects this vertical shift in the graph of my function. So one of the things that we've noticed so far, I think, is that both shifts, both the horizontal shift and the vertical shift, and I suppose I need to also mention in here how to shift downward instead of upward. Don't let me forget that. If I subtracted k instead of add k, I would shift down instead of up. So just want to add that in there for completeness' sake. But what's common to both of these transformations is that both of them are using the same kind of arithmetic. Namely, they're using addition and subtraction. So anytime you think about shifting a graph, this is always going to be a matter of adding or subtracting, the most basic operation in the arithmetic layer cake. And that takes care of our shifts. The next transformation that we want to talk about is a transformation that changes the shape as far as, not the basic shape, but sort of the width or the narrowness or the tallness or the shortness of a graph, but does not in fact change its location. These are called often by mathematicians dilations, and it encompasses both stretching and shrinking, or squishing, as I call it. We're going to have a horizontal flavor. We're also going to have a vertical flavor. As you might expect, as in our last example with shifts, our horizontal stretches and shrinks are going to be affected by things that we do to x, whereas our vertical stretches and shrinks can be things that we do to y, or equivalently, things that we do on the outside of the function, if we want to think about it in a different way, which most algebra textbooks do. So let's think about what it would take for us to stretch or shrink a graph, beginning with a horizontal example of a stretch or a shrink. How do we accomplish a horizontal stretch or shrink? So we're expecting already that this is going to be something that we do to the x variable. So what in particular do we want to do? Let's again start with this y equals x squared basic shape that I have up here. I'm going to single out a point on the graph, let's say 2, 4. Right? What would it take if I wanted to take this graph and, I don't know, let's say I want to make it narrower by a factor of 4. So I want to squish it inwards towards the x-axis by a factor of 4. What would I need to do in order to make that change to my graph? Well, let's think about where the y value for each of the points on my translated graph are going to come from. So if I have a value of 0.5 for x on my translated graph, then to look up this right y value, what I want to do is first multiply that 0.5 by 4 to give me the original x value on my original graph. And then I process that through my function, and then once I process that through my function, I'm going to get the y value that I wanted on my original graph. So just like in our first example of a horizontal shift, let's take stock of what we all had to do in order to get to that place. Thinking about this from the sort of function machine perspective. What I needed to do to look up the correct x value is I first needed to multiply my value of x by 4. So I would put a 0.5 into my function. That number would get multiplied by 4. Multiply by 4 to give me x equals 2. X equals 2 is the x value on my original graph, whose y value I want my new function to spit out. And so then I will apply the f function. And out pops f of 2, which is equal to 4. Okay. So my translated graph needs to first take all the x values, multiply them by 4, and then apply f. And so that composite function is going to have a graph y equals f of 4 times x. So indeed, I've done something to the x variable. Namely, I've multiplied it in place by the number 4. But when I multiplied x by 4 in place, what I ended up with was a horizontal shrink or horizontal compression of this graph by a factor of 4. So what's the general principle that we can take to the bank on this one? We can accomplish a horizontal squish, or I might like to call it a horizontal shrink, of the graph of a function. And the way we can accomplish that horizontal shrink is by replacing x by x times something. So if I replace x by x times a constant, so let's call that constant something. Let's call it c. So if I replace x by c times x, then what I've done is it's going to horizontally shrink or compress the graph by a factor of c. So it gets c times as narrow is another way to think about what's happening when I replace x by c times x. On the other hand, we can also use this same strategy to make our graph wider instead of narrower. All I would need to do is choose a value for c which is less than 1. Because then if I'm shrinking by a factor that's less than 1, I'm not shrinking at all, but in fact I'm expanding. I'm making it bigger. So if c is less than 1, we get an expansion, a stretch, instead of a shrink, if c is less than 1. So, for example, here is what the graph would look like if c were equal to 0.25, 1/4. F of 1/4 times x doesn't make my function a quarter as wide. It makes it a quarter as narrow. In other words, 4 times as wide. So when c is less than 1, my graph gets wider. When c is greater than 1, my graph gets narrower. When c is equal to 1, well, that's my original function. Right? So that's how I can accomplish a horizontal stretch or a horizontal shrink of a graph. Replace x by x multiplied by some scale factor. And that's the scale factor by which it's going to be horizontally shrunken, or if c is less than 1, stretched. So what's good for the goose head ought to be good for the gander as well. Now that we know how to shrink and stretch a graph horizontally, let's figure out how to do it vertically. And it's exactly the same relationship, the same kind of story that we had for vertical shifts. For a vertical shift, we ended up, first of all, making an argument that I should replace y, because we want a vertical thing, by y minus something in order to shift upwards. But then we turned that on its head and said, well, usually what we do is do that same operation with a plus instead of a minus and do it on the outside of the function. Same story for vertical stretches and compressions. So we know we want to do something to the value of y. But what? So let's come back to our y equals x squared example one more time. Let's suppose that I want to take this graph and I want to stretch it out in a vertical direction by a factor of 3. So let's say I want to make this graph 3 times as tall. That's another way to think about it. Well, so any point that I started with in my original graph, let's say 1, 1, I would want its y value to be multiplied by a factor of 3. And when I stretch that out there, that's what I get. The new y value on my translated graph is 3 for the same x value of 1. And that this relationship should hold for all the other points on my curve as well. The y value on the translated graph is 3 times the y value on the original graph. So, how do we make that thing happen with a formula? Well, you feed my function machine a value of x. That very same value of x is processed through my original function. And so if I give this function 2, f of 2 is going to be 4. And then to find the y value on my translated graph, I'm going to multiply that f of 2, I'm going to multiply that 4 by 3 to get 12. So we evaluate the function first, and then we multiply the result by 3. That's how we're going to effect a vertical stretch by a factor of 3. So again, we can think of this in 2 different and completely identical mathematically ways. I can think of this as starting with my basic shape y equals x squared. And if I want to stretch this thing out by a factor of 3, then what I might do is I might try to multiply that y in place by the number, not 3, but 1/3. If I do that, then when, as we do, we solve for y on both sides of this equation to understand what function it is that I'm graphing, I end up back with something I'm writing behind my head here in a neat little trick. I end up with y equals 3x squared. Right? So what have I really done? What I really did was I just took my original function, x squared, and just multiplied it by a factor of 3 on the outside. And that has the effect of stretching out my graph vertically by a factor of 3. So we'll say it in 2 different ways, just like we said it before when we were talking about shifts. In order to make a vertical stretch or a vertical compression, what I want to do is, on the one hand, replace y by y divided by, what do I call this number? Let me call it b. If I replace y by y divided by b, then what I get is a vertical stretch. Stretch vertically by a factor of b. But replacing y by y minus b and then resolving my equation for y, as we usually do, shows us that it's really the same thing as just multiplying by b on the outside of my function. Outside of f of x is going to shift vertically by a factor of b. So again, just to recap, the original graph, the red dotted line here, has the equation y equals x squared. If I want the version of that graph, if I want the version of that graph which is stretched out vertically by a factor of 3, I just want to take my x squared and multiply that x squared on the outside by a factor of 3. That gives me exactly the graph that we had right there. So now we know how to shift horizontally and vertically. Shifting is always a matter of addition and subtraction, and a horizontal shift attacks the x. A vertical shift either attacks the y or it attacks on the outside of the whole function. And for stretches and shrinks, rather than being matters of addition and subtraction, stretches and shrinks are matters of multiplication and division. In the case of a horizontal stretch, we multiply or divide the value of x in place. And for a vertical compression or expansion, what I would do is multiply or divide either the value of y in place or the value of the entire function on the outside of f of x. So there is the lowdown on stretches. So we have one more type of transformation to talk about. And this is, in a way, I think the most interesting from a mathematical perspective. And those are the flips. How can I take the graph of a function and flip it, reflect it over an axis of symmetry? How do I accomplish that by doing something to the formula for that function's graph? So let's start with the horizontal example. I want to accomplish a horizontal reflection of a graph. How am I going to make that work? So to do this, let's again go back to just a piece of graph paper here. I've got a graph sitting on it. And the question that I'm trying to ask myself here is, how could I reflect this graph in a horizontal fashion? And what I mean by that is, how could I flip it over the central vertical axis of symmetry of the xy plane? In other words, how can I flip this graph over the y-axis and get its mirror image? If I were to do that, it would turn this original graph, which is the graph of this quadratic function, x squared minus 6x plus 9. If I flip it over the x-axis, over the y-axis, a horizontal flip over the y-axis, then what I get is something that looks exactly the same. It looks like a parabola again. It's just on the other side of the y-axis instead of on the right side. It's on the left side. That's where the vertex lives, for example. And any point on my original graph is going to have a point on its mirror image, the translated graph that it corresponds to. For example, on my translated graph, the x value is -5. That corresponds to, on my original graph, the x value of +5. So how have we accomplished a reflection of my graph across the y-axis? In other words, what I call a horizontal reflection. All I've done is I've replaced x. After all, this was a horizontal transformation, and so it was some replacement that we make to x. I've just replaced x by -x instead. Just replace every x value that we started with by its opposite. And when I do that, I get what I call the horizontal reflection, or the reflection across the y-axis of my original graph. So that's a pretty quick one, right? And because that one's so quick, you can expect that the next one, and it's the last one on our chart here, is going to be similarly quick. It's going to take the same approach, but it's going to apply that approach to the y-coordinate instead of to the x-coordinate. How do I accomplish a vertical reflection? In other words, a reflection across the horizontal axis of my Cartesian coordinate system. So if to flip a graph horizontally, we flipped the sign on the variable x. To flip it vertically, what do you think we need to do? Yeah, flip the sign on the coordinate y instead. Let's just verify that that works. So here's again my original graph. This time it's just plain old vanilla f of x equals x squared again. If I want to flip the sign on all my y coordinates, then it means that on my translated graph, the x coordinates correspond exactly. So the x value of 2 on my original graph corresponds to the x value of 2 on my translated graph. But it's the y-coordinates, 4 and -4 respectively, that are interchanged. They are the opposites of one another. And that is how I've reflected this graph across the x-axis, or what I call a vertical reflection. I've just replaced y by -y. And so we can think of that as being the secret to what we've done here. But then, just as with our other vertical transformations, we'll also give another way to think about this that's a little bit more usual when it comes to the textbooks that teach pre-calculus. So replace y by -y, and I get a vertical reflection, a reflection across the central horizontal axis of the Cartesian coordinate system. But another way to see this. So let's go back to the example that we had up here, right? This is the graph y equals x squared. That's my original. When I replace y by -y, it does have the right effect. It flips that graph over the horizontal x-axis, right? So it's a vertical reflection. But the way in which we're accustomed to seeing that is just by multiplying both sides of this equation by -1 to move the minus that's attached to this y over to the other side of the equation instead. So y equals -f of x. And that is how we accomplish a vertical reflection by operating not directly to the y, but to the outside, if you like, of the function itself. So, or just multiply, another way to think about that, multiply by -1 on the outside of my function. Outside of f of x. So, in summary, all of the graph transformations that we can do, let me just put here change sign, all the graph transformations that we are going to learn how to do in pre-calculus relate to one of these three different types. A shift, so the rigid translation, a mathematician would call it, of a graph's location inside of the xy plane. And that covered things like horizontal shifting, in which we add or subtract a quantity to the x value. It covered vertical shifting, where we add or subtract a quantity to the y value. And that covered both of our two different kinds of shifts that have to do with adding or subtracting, respectively, to the x variable or to the y variable. The second kind of transformation that we looked at were the shrinks and the stretches. These are things that don't change the location of the graph so much as they change the width, narrowness, tallness, or shortness of a graph. And they came in two flavors, both of which incorporate multiplication and division as the type of arithmetic. In the case of a horizontal stretch or compression, I'm multiplying the x value directly. If I multiply x, the variable x by 2, replace x by 2x, I'm going to get a twice as narrow graph. If I replace x by x times 1/2, I'm going to get a wider graph by a factor of 2. So multiplying x directly, replacing x by a constant times x, is going to give me a horizontal stretch if I'm multiplying by a constant that's less than 1, or horizontal shrink if I'm multiplying by a constant that's greater than 1. Same type of story happens on the vertical side. That for a vertical stretch, or a vertical squish, if you like, what I'm doing is multiplying the value of y by a constant instead, which has the effect of multiplying on the outside of my function's formula by a constant. If I replace f of x by f of x times 2, I'm going to get a graph which is twice as tall as my original. If I replace it by f of x times 0.1, I'm going to get a graph that is can't quite do it, by 0.2, let's say. No, I guess I can do it, 0.1. I'm going to get a graph that's squished by a factor of 10 towards the x-axis. And then finally, we can use a graph transformation to either take a graph and flip it in a horizontal fashion, flip it across, reflect it across the y-axis, and we do that by replacing x by minus x. When I replace x by minus x, my original graph gets flipped over the x-axis to become its mirror image, over the y-axis, to become its horizontal mirror image on the other side of the y-axis. And in the same way, if I want to reflect the graph across the x-axis, so reflect it vertically, I can replace f of x by minus 1 times f of x. Just switch the y's sign. And when I switch the signs on the y's, I get the mirror image of my graph where it's been reflected vertically instead of horizontally. That's our full list of graph transformations. And it's actually those last two, it's the reflective transformations that we're going to use in the last portion of our live stream today to talk about what it means for a function to be even or for a function to be odd. So that's going to be our last thing that we do. But before we go there, what I want to do to wrap up this graph transformations portion is just solve a little mystery. So let's look at an example problem. And in this example problem, what I want to do is I want to cook up a graph, basically. And when I cook up this graph, I'm going to ask you, or I'm going to solve this problem, so I guess I'm asking me. We want to figure out how to find a formula for that graph without relying on technology or doing something really super fancy. So I'm going to quickly cook up a graph here. Let me just come up with a nice example. All right, so here is here's the graph that we're going to look at together, except before I show it to you, I want to figure out a way if I can, all right, I'll just do it this way. So here's the graph that I want us to look at together now. And maybe I'll keep the graph paper in here. So here's a graph, and the question that I want us to solve together is, how do I find an equation for this graph? Well, the first thing that we might want to do, the first step in finding an equation for a graph without using anything super technological and fancy, just using what we know about transformations. The first task is just going to be to go back to our catalog of basic shapes of graphs and see if we can match up the graph that we're looking at with one of the basic shapes from our catalog. What does my graph look like? Well, it consists of these sort of two line segments, and they're meeting at sort of a pointy cusp up here. We could even put coordinates on that cusp if we want to. That's going to be important for later. It meets up at 3, 6. But it's these two line segments, one of them increasing, the other one decreasing, and a sharp point in the middle. Well, which one of our basic shapes looks like that? It's the absolute value function. F of x equals the absolute value of x. So with that in mind, what we want to do is take the absolute value function as our prototype and then see if we can't sort of massage that absolute value function into place in order to get it to have exactly the location and exactly the shape and size that we want it to have in the end. So going back to our graph paper for a moment, in the black dotted line here is the graph of the standard absolute value function, y equals the absolute value of x. So we're going to have to do a few steps in order to get this graph to be where we want it to be. Let's do that by labeling a couple of what I sometimes call control points. Just points that have nice, easy coordinates on our graph. So one example point might be 0, 0 on my original graph of the absolute value function. If I can trace where that point 0, 0 goes in my various transformations, then I should be able to figure out how to get it to go where we need it to go. So with my absolute value of x up here on the graph paper, what I want to do is first, let's think about how we might here. So on my original graph, I'm going to label, let's say label 2 points. I'm going to label 0, 0. I know you can't see this, you will in a second, and 1, 1. So I'm going to label those two original points on my absolute value graph, 0, 0, and 1, 1. And then what I want to do is I want to label the corresponding points on my new graph that we're looking at the end of the day, the graph that we're trying to find the equation of. And the 2 points that I can see that correspond to it are 3, 6. That's the pointy part on this absolute value graph. So that corresponds to the pointy part at 0, 0 on my original graph. Again, you'll be able to see this in a second, 3, 6. And then it also looks like there's a point that I can label, 5, 5, that seems like, and I'm going to be kind of dodgy about this for the moment, kind of seems like it should correspond to my other original point on the original absolute value graph. So here are the points that I think are going to kind of correspond to one another. This 0, 0 point here is going to correspond to the 3, 6 point. That's the pointy part. And then the 1, 1, which is laying right here on my original graph, I think is going to correspond to 5, 5 on my new graph. But that's just sort of, that's just speculation. So indulge me for just a moment to adjust my browser window, because I want to play around with this graph without you seeing the formulas that I'm typing. So why don't we do it this way? I'm just going to kind of put a little mask over here for a second so that you can't see what this formula is I'm about to whip out. There we go. So you can't see it, but I can. All right, so let's think about what it's going to take to move this basic shape graph into the red graph that we're trying to look at here. Well, the first thing I want to do is I want to do my stretching and I want to do my shifting. Let's keep track of what I'm doing over here in the note. First thing I want to do is either a horizontal or vertical stretch or shift. And I want to think about it this way. If I compare my two original control points, 0, 0, and 1, 1, those are separated by an x distance of 1 unit. They're an x distance of 1 unit apart. Whereas my two corresponding points here are 2x units apart. So let me try to do a stretch horizontally by a factor of 2 as my first transformation that I do to this graph. Well, how do we accomplish that transformation? Well, remember, to stretch horizontally by a factor of 2, according to our little chart of transformations for today, to stretch horizontally by a factor of 2, I want to not shrink, so I don't want to use a c that's greater than 1. I want to stretch, use a c that's less than 1. And if I want it to be stretched by a factor of 2, then the c that I want to multiply by x by is going to be 1/2. So if I replace x by 1/2 times x, then what that should do is it should stretch out my graph horizontally by a factor of 2. And sure enough, that's exactly what it just did. Right? It took my original absolute value, black dotted line graph here, and it stretched it horizontally by a factor of 2. Great. So now my new graph looks like it has the right basic shape. But it's not pointing in the right direction. My graph is still a V. What I want is an upside down V. So let's make our next step the step in which we flip this graph upside down. So I want to reflect vertically. In other words, I want to flip this graph over the central horizontal x-axis of the xy plane. How do I do that? Well, I should replace y by minus y. Or equivalently, place a minus sign on the outside of the entire graph of my function. Either one of those does the same thing. So now I stretched horizontally by 2, then I reflected my graph vertically, and now my graph has the right shape, the right size, the right orientation. The only thing it doesn't have is it doesn't have the right location. So let's move this central point right here, this 0, 0. Let's move it so that it lines up exactly with its corresponding pointy part of my translated graph. So in order to do that, we have to do two things. We have to shift both vertically and horizontally. Just for fun, let's shift vertically first. Let's shift it up. How many units do we have to shift it up? Well, the original graph has this point at 0, 0. The new graph has it at 3, 6, and that's a y distance of 6 units up. So I want to shift this graph up by 6 units. How do I do that? Well, I either subtract 6 from the y, or, the way we're usually accustomed to doing it, add 6 outside of the entirety of my function. That'll be the way that we probably want to leave that one in. Okay. So now I've shifted my graph up by 6 units. All I have to do now to get to my last step is move this graph to the right by 3 units. So one last shift will get us home. Shift horizontally. Right by 3. If I move this graph to the right by 3 units, we'll get where we need to go. How do I move a graph to the right by 3 units? I can move it to the right by 3 by replacing x by x minus 3. So wherever I see an x, I replace it with an x minus 3. That will give me the horizontal shift to the right that we're looking for. X minus 3. Done. And there it is. My green graph now lines up exactly with the red graph that we were trying to solve for in the first place. And so there is an equation that describes my translated graph. And before we wrap this example up, I want to make a note here about an intentional set of choices that I made. And that is the choices to leave shifts until last. Because I don't want to move the location until after I'm done stretching, shifting, and reflecting all the rest of my coordinates. Because if I move the location first and then I stretch, the location is going to change when I stretch. Yeah. So it's just like following the order of operations. So think about it with from the PEMDAS lens, right? Do all your multiplication and division before you think about adding and subtracting when it comes to graph transformations. For me, that's just the way that I keep everything as straight as possible. You could, if you wanted to, do some algebra to simplify this equation, but I think we'll skip that. We got what we came for here. All right, so with all of that, let's take our last step forward into thinking about symmetries of graphs. So we know now how to translate, how to apply transformations to graphs in a lot of different ways. But the ones that are most important for thinking about symmetries of graphs are the last ones that we talked about, the reflective transformations, the flip across the y-axis that we get when we replace x by minus x, and the flip across the x-axis that we get when we replace y by minus y. Those two we can use to define types of function symmetry. And the first type of function symmetry we're going to talk about is a function symmetry called evenness. So what does it mean for a function to have even symmetry? Here's an example of a graph of a function that has even symmetry. And what makes it have even symmetry is the fact that the right side of this graph is the mirror image of the left side. And another way to say that is if I take this graph and I reflect it across the y-axis, I get the same thing as the original graph. If I take the right half, I reflect it over the y-axis, I get exactly the left half. So that is what it means for a graph to have even symmetry. For every point on my graph, there is a corresponding point that has the same y value. Take a look at the y values here are the same, but have opposite x values. So for a function to have even symmetry, maybe I'll just type this in here. So f is an even function if the same y values have opposite x values. Actually, that's kind of a backwards way to say it. Let's say it the other way. If opposite x values have the same y value, right? Negative 1.6 and positive 1.6 are opposite x values, but their y values are the same. And that's true for every set of points on this graph. So that's what it means for a graph to have even symmetry. What does that mean for the sake of the original function? What does it mean from an algebraic perspective? Well, remember, what we're doing is we're really reflecting this graph across the y-axis. And when I reflect the graph across the y-axis, I get the same graph as I originally had. But how do you reflect the graph across the y-axis? You replace x by minus x. So another way to think about this is to say that if I replace x by minus x, the graph that I get is exactly the same as the graph of f of x itself. So just to underscore the point here, my original graph in red is y equals f of x. My graph in green is y equals f of minus x. But those two graphs are identical when a function has even symmetry. And therefore, because they're graphs of the same function, we conclude that f of minus x and f of x are actually the same function. That is what it means for a function to have even symmetry. So I'm going to kind of record that here on the screen real quick. And what I want to do before we're done with today's live stream is an example of looking at this from an algebraic perspective as well. F of minus x equals f of x. That's the algebraic perspective. And the graphical perspective is symmetry over the y-axis, horizontal reflective symmetry. So that's what it's going to mean for a function to be an even function. What about an odd function? What do odd functions have in the way of symmetry? Let's look at a graph that has an example of odd symmetry. So here is a graph of a function, happens to be x over x squared plus 1 is the expression that defines f of x as a function. This graph is said to have odd symmetry. Now notice, it doesn't have a reflection symmetry that we can speak of, at least not a single one. Right? If I were to take this graph, for example, and reflect it across the x-axis, if I reflect it across the x-axis, what I'd be doing is taking y equals f of x and just replacing y with minus y, or replacing f of x with minus f of x. But if I flip this graph vertically, we get a different graph. Similarly, if I flip this graph horizontally, we get a different graph. But not that different. In particular, what we notice is that the graph that we get when we flip the original horizontally and the graph that we get when we flip it vertically are exactly the same graph. And that is a very peculiar kind of symmetry. So peculiar that we call it oddness. So a function has odd symmetry in its graph if its horizontal reflection is the same as its vertical reflection. Right? So this example that we're seeing here is such a thing. Here's the vertical reflection, and there's the horizontal reflection. Right? And those two graphs are exactly the same. What does that mean from an algebraic perspective? It means that the horizontal reflection, which is the graph of y equals f of minus x, and the vertical reflection, minus f of x, are exactly the same. And so a function has odd symmetry if it satisfies this functional equation. F of minus x is equal to minus f of x. F of minus x equals minus f of x. And then we get horizontal reflection is the same thing as vertical reflection. There's actually one other way to think about what odd symmetry really means. Okay, The one other way to think about what odd symmetry looks like is we can think of it as, rather than reflection, because we're talking about two different reflections, we can think of it as a rotation instead. So I kind of like this viewpoint of odd symmetry as well. This graph has odd symmetry because if I take the part of this graph which lies to the right of the origin here, and I reflect that piece 180 degrees around the origin, I get the same thing as the other part of my graph. So if I just take the right side and rotate it by 180 degrees, I get exactly the left side. So we can also think of this as a rotational symmetry by 180 degree rotation, instead of thinking about it as two separate reflections. That's what we call odd symmetry. And it gets borne out in algebra by f of minus x equals minus f of x. The sort of spiritual way that I think about what these functions are doing is that odd functions don't see sign. Sorry, even functions don't see sign. If you switch the sign on an even function's value of x, it doesn't notice. The y value remains the same. So even functions don't see sign, whereas odd functions completely reverse sign. If I switch the value of x, the y value necessarily switches as well. Completely switch. So in a way, these are two opposite ends of a spectrum, right? An even function, if I change the sign on its x value, nothing happens. For an odd function, if I change the sign on its x value, the whole y value switches sign. Okay. Let's take a moment to wrap things up today to look at the examples that we just did of even symmetry and odd symmetry, and try and convince ourselves with algebra why these functions are respectively even and odd. So the first example that we did, this was my even function. This is the function f of x equals the quantity 1 minus x squared, that whole quantity squared. And let's suppose that I wanted to show that that's an even function. How would I do it? Well, we just have to follow the recipe that's up here. Replace x by minus x. In other words, reflect my graph over the x-axis. Sorry, over the y-axis. Reflect it horizontally. Replace x by minus x. And then what I should get, f of minus x. If my function is to be even, then what I get when I replace x by minus x should be exactly the same thing as I originally had. So that minus sign on the x needs to just disappear. That's the goal. Let's find out if it actually works using the algebraic perspective. What is f of minus x if f of x is 1 minus x squared, the quantity squared? Well, replace my x by some minus x in parentheses, and then try to simplify this expression. But when I simplify this expression, this power of 2 gets applied inside the parentheses, both to the x, but also to its coefficient. Its coefficient is negative 1. So when I square the quantity minus x, what I get is minus 1 squared times x squared. I'm going to be really explicit and write this out here. So I'll get minus 1 squared times x squared. But what is minus 1 squared? It's minus 1 times minus 1. Namely, it's just 1. So I have 1 minus 1 x squared. That quantity squared. But multiplication by 1 is an invisible operation. We can just get rid of it. And now, take a look at what I have. I have exactly the same as my original function. So this is why, from an algebra perspective, we know that this function is even. When I replace x by minus x, the result after it's simplified is just exactly the same thing as the original function was. So that was our example for even symmetry. Let's close things out by doing the example for odd symmetry. So here, we start with the function f of x equals x over x squared plus 1. And let's suppose that I want to use the formula there to show that this is an odd function, that the function and by extension its graph have odd symmetry. What am I going to have to do there? Well, again, follow the recipe. Replace x by minus x. So that part of the strategy is the same for testing both for even symmetry and for odd symmetry, okay, regardless. The difference is what I'm going to start looking for after I replace x by minus x. So here, if I replace x by minus x, in order to show that this function is odd, what I need to get at the end of this process is not f of x, but indeed exactly the opposite of f of x. That's what it's going to take to show that this is an odd function. So let's go through the motions. If I replace x by minus x in this expression over here that defines my function, then what I'm going to get is minus x divided by the quantity minus x squared added to 1. So I've replaced x by minus x everywhere I see it in my function. And now we're going to do that same simplification that we did before in the last example, where this second power distributes to the minus sign as well as to the x, and I'm going to save us the extra step here and just write the minus 1 squared as positive 1, and therefore it disappears. But then take a look at what's happening in my numerator. Up here, the x, the minus sign that this x has brought to the party, actually has nowhere to go. It doesn't go away. In fact, it just survives. And we end up with this minus x in the numerator. But fractions working how fractions work, we could notice that multiplying by negative 1 up in my numerator is actually the same thing as multiplying my whole fraction by negative 1. Right? And then when I look at this expression, I see a piece of it right here, x over x squared plus 1, that is in fact exactly the same as my original function. And so that accounts for my f of x. But this minus sign out in the front there is what shows that this function does indeed have odd symmetry. When I switch the sign on my x, I also end up switching the sign on the whole function f of x. In other words, switching the sign on my y's. So that's going to wrap things up for today. We've seen, both from a graphical and an algebraic perspective, how to understand transformations of graphs. And that understanding just breaks down to 3 different types of transformations. Shifts, which we get by adding or subtracting to my x or y. Stretches and shrinks, which we get by multiplying or dividing my x and y. And reflections, in which we change the sign on our x's or y's. And it's that last type that also let us define symmetries of functions. Even symmetry, in which if I reflect over the y-axis by replacing x by minus x, nothing changes. And so my graph has symmetry over the y-axis. That's what we would call an even function. And then odd symmetry, in which when I replace x by minus x, my entire function changes sign at every single x value. There we get a kind of symmetry called odd symmetry. And on a graph, we can recognize it by one side of the graph rotated by 180 degrees around the origin gives me exactly the other side of the graph. That's what we would call odd symmetry. And we can test for those kinds of symmetry just by using these algebraic functional equations. The last point I want to make to wrap up is that not every function is one of these two things. Unlike with whole numbers, where every whole number is either even or odd, not every function is either even or odd. There are plenty that are neither. And so it's actually kind of rare for a function to have one of these types of symmetries. Most of the time, they have none of the above. If I just draw a random graph, it's not going to have a nice symmetry property in general. But a lot of the friendly graphs that we work with and the building blocks of other functions do have these types of symmetries. And so they're worth studying to help us learn how to do things with the equation of a function that affect reflections on the graph. That's going to be where we wrap up today's live stream. Now that we've kind of exhausted our understanding in the context of functions and graphs, the next places that we're going to start to go is we're going to start looking at different types of functions and how the various parameters of those functions can conspire to model behavior that we can measure or observe out in the real world. So that's really where the functions modeling change aspect of our course is going to start to hit the road when it comes to modeling. So our next set of topics is going to deal with linear functions and how to understand what linear functions are, how to spot linearity, what makes linear functions tick, what do their graphs look like, and all that wonderful stuff is where we're going to go next.